Okay, let's talk. First of all, the take-home exam that you picked up should be problems 1 through 7, but there's 2 number 7s. You've what? What the hell? What the hell happened here? Wait, there's number 1, number 2, number 3, number 4, number 5, number 6, number 7. What do you have on the back of this? 6, 7.
So 6 is repeated.
Yeah, I just have to like the same number 6, but they're all there.
6 and then 7.
So 6 is just repeated.
Is 6 repeated? Is that what it is?
No, 2 for me is repeated.
All right, so let me tell you what you're supposed to have on the mini exam. Let's all agree on this. The first problem is area under a curtain, or the area of a curtain, yes? Next problem is man, that got all messed up. A wire, right, shown, find mass, find center of mass. The third problem should be calculate the work, right? Fourth problem, blah, 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 is a conservative vector field, parts A and B. Number 5, that picture with the little, like a doorway, arch doorway, right? Number 6, blah, 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 is the velocity vector field for a flowing fluid, yes? Okay. And then what? Okay, number 7 is that the same? Same problem as which one? Yeah, something got all screwed up. Okay. Yeah, you should have 7 problems. All right, just any questions? What are you missing? This one?
The 3 and 4 missing.
What a clusterfuck. You know what I'll do? I'll email out the test today and make sure everything's numbered correctly. But I mean, if you want to start working on the problems, those are problems you can at least start with. All right. I don't know what the copier did today, but I've never seen it mess up so bad. All right. The next order of business is everyone has the copy of the notes, right? If you want those bound, again, just come by my office and you can do this to it. I do want to talk a little bit about the take-home exam that I just handed back. There was one particular item that I took off on that I thought I would address, and it was the problem. Where was it? See if I can find it. Can I see one of your tests? Can I see it real quick? I think it might have been the first one. Acceleration. Where the particle's moving. Mini exam 3. It was the problem where number 1 where it says find the values of t where the particle which moves along this curve has a maximum speed. Right? Yes? You know what I'm talking about? Okay, so a lot of you did it correctly and got to what I'm about to show you. Got to taking the derivative, right? When you took the derivative, you should have got something like negative cosine t sine t negative 2 sine 2t. That look right? Yes? Okay, that should be it. Now, that represents the velocity, right? That's the velocity vector function for this moving particle. How do we find the maximum speed? So speed is defined to be the magnitude of this derivative, right? So you just got to take the square root of, each of those components squared, whatever, work that out, right? And that's going to turn out to be something, I believe it was it 1 plus, was it 4 sine squared 2t? Okay. So, and then you're supposed to go and try and find the maximum of that on a closed interval. I believe it was 0 to what, 2 pi? Yes? Okay, so at that point, what I wanted to see was that you would go back and do like Cal 1, where you take the derivative of that, find the critical points. Okay, what I saw a lot of students do was, instead of doing that, looking at the acceleration function, right, which the acceleration vector function would be the derivative of this, right? And then trying to figure out where the acceleration was 0. Is that what some of you did? No? No? Okay. So my question would be, if your acceleration is 0, does that mean you have to have maximum velocity? That's why I wanted to clear this up. What do you think? Uh-huh. But where the acceleration is 0, does that tell you that you're at a place where you have maximum speed? Well, that's what I'm asking. Where does that come from? Where is that logic coming from? Okay, so let's look at a graph of something. All right, let's say this is time, and let's say this is speed or velocity. Let's do two-dimensional, okay? So if I go like this, let's just say my maximum speed is happening here. Do you agree? I mean, on some closed interval. If I close it off in here, right? That's my maximum speed. Now, what's happening there is that that's where my derivative, I'm just going to say r prime is equal to 0. Agreed? Where is the second derivative on this graph? Where's the second derivative equal to 0? And the inflection point, right? That's here. Mm-hmm. Well, yeah, we can say speed. What are you? First derivative. Yes, the first derivative. Okay, this is position. Right? Look, hold on. Let's back up. Let's say we have a graph that gives us time and gives us position. All right? Position. Now, this is going to be a little more difficult to draw, but, well, let's just do something like that. Then if we take the first derivative, this is going to be position, right? If we take the first derivative, we get the speed, right? So first derivative of this, what we have is, positive slope here means positive derivative until we get to this point here, right? Then we start getting negative derivative. So we'll have like positive derivative. It'll be pretty high. It'll come down and it'll be negative something like that. Okay? So where on this graph on the left side, what does this point right here represent? That's when the first derivative is 0, right? And that would represent this point here, wouldn't it? So first derivative 0 here gives me where I have what? First derivative, speed is 0. Yes? Second derivative would be what? Acceleration. Where do I have that happening here? Let's say right in there. Does that look good enough to you? What I'm trying to understand, because I took off for people who set acceleration to 0, because I wanted to see what the argument was as far as why is acceleration equal to 0 going to give you maximum speed.
You just take everything like a new function, like the speed function is now your position function, and you want to maximize that.
Okay.
Then you just take the derivative. So acceleration is arbitrary.
Okay, so you took the derivative of, but you took the derivative of the velocity, right? Okay, so the derivative of velocity gave you a new vector function, right? Exactly. So we started with our position. You took velocity, which was the first derivative. Then you took acceleration, which is second derivative, right? Okay, but why does acceleration equal to 0 tell you where you have max speed? That's what I'm not convinced is true, because your speed is a magnitude of a vector, right? The speed is a magnitude of a vector. Your acceleration is a new vector. And to find out where that's 0, right, that's what you did, set it equal to 0, you have to set each component equal to 0, right? That's different than taking the speed function, which is this thing up here, the square root, right, of this part here, the magnitude of it. That's speed. That gives you something that you can find the maximum of. This doesn't necessarily give you the same result as this. It did in this problem, but it doesn't in general. If you look at a picture, this again, I'm trying to show that where you have inflection points won't always guarantee max speeds.
But it's hard to tell velocity from looking at a position graph. So
that's right.
When you get you take the derivative and you get the points on where you find the max and min on the velocity graph, it'll tell you where it changes direction, right?
Okay.
So once you have those points, then you're at the component, it's a new vector. Then you have to plug them in and see which one gives you the highest value.
Okay, let me mess with it a little more, because when I graded it, I was like, don't think this is going to work, but I'm not sure. So that's why I wanted to bring it up. I took off, I think, 5 points for anyone who did it. I'm going to look into it some more, but I wanted to hear the argument as to why, if you had seen that somewhere. I mean, because directly doing it, it's just look at the velocity vector, take its magnitude, that's speed, and then find when that's biggest and smallest. But taking the acceleration vector function and then setting each of those components to 0, not sure that's going to lead us to the same exact thing. So I'm trying to find a counterexample of one that won't work that way. So I'll work on it some more. If I can find a counterexample, then everything will stand. If I can't and it turns out to be true, I'll be happy to reward those points back. Okay? Yes? That's the way it was. You're supposed to, well, not supposed to, but the approach I was looking for was take its derivative, right? Look at that as its own function, take its derivative, and then find out, what the critical points are. So you take the derivative, you set it to 0, and you come up with like, how many were there? How many critical points were there? There's 5 of them, and then you have to test each of those 5 and figure out what the biggest and smallest was. And that would mean you have to solve a trig equation, a general trig equation for that. So it was like, was it sine 2t? Or yeah, you had to just solve that on the interval 0 pi or 2 pi? 2 pi. And that had, what, 5 solutions or something like that? Was it 0 pi? Okay. All right, well, I don't want to spend any time on that, but just know the people who I did take off on that, I'm looking into it a little more. All right, today, what are we doing? We're going to finish up chapter 12 and then get into 13. So, chapter 12, section 8, titled Change of Variables, is a way of generalizing what we did before. Remember when we converted to polar and we always had to put in that r in the integral, and then we saw last class when we convert to cylindrical, we had to put an r in our triple integral. When we convert to spherical, we had to put the rho squared sine phi. This section talks about, in general, if you want to convert from any coordinate system to the other, how can you do it? And what will appear in your integrand. So the notes go through and they go through and explain where polar comes from. It talks about how you can make the conversion over, and then it defines this thing. I'm on this page where it has the areas approximately this vector function r, partial derivative with respect to u, cross with partial with respect to v, and then this delta u, delta v. I don't want to go through this whole thing because it's a little bit tedious and time consuming. I have a video from the spring. If you go back in the YouTube channel where I go through it in depth, you can watch it. But I can check on that. I can check. Get back with me. But the idea is this. This picture shows the main idea. We take some region that would be very hard to possibly convert to, type 1, type 2, or polar. It would be difficult to integrate over, and then somehow change our variables so it turns into a very nice region, like this rectangle. So what I want you to notice, let me see. There's a little point here. Can y'all see my little point on there on the graph? I'm going to zoom out here. Oh, that doesn't look good. You can kind of see it this way. I have a green arc here. That green arc, when I do my change of variables, gets turned into this side of this rectangle. And then this black line here, when I do my change of variables, gets turned into this black line here. And so every point in this region gets mapped over to this over here. It's called a linear transformation. So we're transforming one region into a nice one. Once we convert over, this is just a basic rectangle, and they're easy to integrate over, right? So that's the idea is, can you get something that's difficult and switch it into something that's easier? A good example of this would be when we first started talking about polar regions. If I wanted to do this region right here, I mean, we would have to make that a type 1 from when we first were talking about double integrals. We would have had to have broken it up into these two pieces, two regions, right? Because we would have had, on this first piece on the right, we would have had a top function, and then the bottom function would have been 0. And then in this, to the left, top function would have been this circle, and then this circle underneath it, right? But by doing it in polar, if let's say this radius was 1, even though this doesn't look right, and this was 2, then when we convert to polar, it was very simple, wasn't it? Theta was stuck between what? Here would be 0 and pi over 2, and then r was stuck between 1 and 2. And that's it, right? So just like this picture is showing in the notes, complicated region turns into your two new variables stuck between constants. That's what we're going for. So, but how do we do it? Well, to do it, we have to, at the end of it all, use this formula right here. All right, it's what's happening is you start off with variables x and y. You're integrating over region D with respect to area. You now are going to do a double integral over S. S is the new region that you've transformed your ugly one into. So it's gone from the ugly one D to the new one S. You've also changed your variables. X is now a function of two new things. Y is now a function of two new things. What was that for polar? When we use polar conversion, what was X? It was R cosine theta, right? Well, R was a new variable, right? And theta was a new variable. This formula is more general. It's just U and V. So if I would replace the U there with R and the V with theta, then X is a function of R and theta. And then the Y, same thing. For polar, it's Y is R sine theta. And then we had that weird thing. For polar, this was just what? That piece right there was just the R. But what it's going to be, in order for us to determine it in general, it's this thing called the Jacobian or Jacobian determinant. It's the partial of x with respect to u times the partial of y with respect to v minus partial of x with respect to v times the partial of y with respect to u, magnitude. So we have to compute that. All right? And that will give us our converted integral. So what I'd like to do is I'm going to skip this example. This example is not very natural. The book does this. Okay, it's their first example. If you want to do this, read through it. What the problem with it is that they spend a lot of time in the book first showing you that this region that's weird gets mapped over to this rectangle, and then they do the problem. It takes a while to show you that that's true. So I'm going to skip that, read through the book, and go to a different example. So I'm going to start with this one. But I think before I do it, let's just show you. Let me show you that Jacobian determinant, how it works for polar coordinates, just so you can see it does work. All right. So let's say we want to go and convert to polar coordinates. All right, so what are our conversions? We say x is equal to r cosine theta. We say y is equal to r sine theta, right? Now what I'd like to do just to show you how things work with the formula, can we do this instead? U cosine v, and then over here, u sine v. So I'm just replacing r with u and theta with v, just so I can use the general formula. Does everyone see here also that x is now a function of u and v, right? Y is now a function of u and v. So if I had an integral that started out as double integral over d of f of x, y, dA, if I want to convert that into this new region, I'm told that it should be replace the x with your function of uv, replace your y with your function of uv into your function, and then in here, your Jacobian determinant, right? Yes? I'm just going to put Jacobian determinant like that. So let's compute the Jacobian determinant real quick. What is it supposed to be? This is what we're doing, right? This is it right there? Okay? So these are the two equations I'm going to be using right here, right? So what is the partial? Let's just get all four things first. What's the partial of x with respect to u first? What is it? Cosine v? Everyone okay with that? Taking the partial of this equation right here with respect to u. Okay, and then I'm supposed to multiply that by what? Partial y with respect to v, which is u cosine v. And then I'm going to subtract from that partial x with respect to v, which is negative u sine v, and then I'll do partial y with respect to u, which is sine v. Yes?
Basically taking the cross product of the gradients of the two functions, but why does that, why does that work?
Okay. Remember I said in the beginning, I explain it. There's a little hand waving that I have to do because unfortunately this uses a little bit of what are called parametric surfaces, which we haven't looked at parametric surfaces yet. And so you have to understand a little bit about that before you can understand the actual reason it works, which is why I kind of go, eh. But if you look through the notes, I can show you with just a basic idea, all right? And I'm going to have to stay pretty basic. You see that region right here? We're trying to get like in the infinitesimal area, right? Okay, so this vector right here and this vector right here create a parallelogram. The magnitude of that parallelogram is its area, right? The thing I would have to convince you of is that this vector is the change in v times, the change in v is like a scalar, times the vector, the partial derivative, the partial of r with respect to v. But what the hell is r? R is what? Right? R is, I mean, what's r? All of a sudden I've thrown r in here. R is actually the vector function that creates this surface. So it's what we call a parametric surface. See, r will draw me this like plane. So the partial in one direction, partial in the other direction, you scale them by the infinitesimal, and then you get the area of that, which is a cross product, right? If that helps. I know. Absolutely, it will depend on your. It will vary, but your surface. See, this is where I define. Right here, it can be shown that r of uv is this vector function. I'm waving at my hands. It's somewhat difficult to understand at this point because we haven't looked at parametric surfaces. See, we can draw surfaces with parametric functions instead of curves through space. And that depends on your change of variable.
Right. Yeah, it makes sense conceptually. I just want to see it rigorously. But it's probably in the book.
Yeah, I mean it's you can look at the book. I think it has the working out of all the details. But again, it still draws on stuff from later in chapter 13, so it's yeah. Okay, so compute this Jacobian determinant. So I'm just going to say JD down here. And let's do the magnitude of it right now. So I'm going to do the magnitude of, what do we have? These two multiplied, which gives me what? U cosine squared V. Minus these two multiplied, which gives me minus minus, right? So plus U sine squared V. And I can factor a U out, right? And cosine squared V plus sine squared V is what? 1? So you just get what? Magnitude of U? Which is just U. As long as U is positive here, right? We're good. Just U. And what was U? U is R. So the thing that pops into the integral will be R if you go and do a polar conversion. All right? Now, how would things change if you wanted to do spherical? It's a little more complicated, right? This Jacobian determinant becomes a little more rigorous, a little bit more involved because now you've changed x, y, and z to something instead of just x and y. Let's do this example first, though. Okay, everyone have this? Use the change of variables. So instead of saying x is r cosine theta, y is r sine theta, we're going to do this. We're going to say x is U squared plus, oh wait, hold on, this is not the one I want to do. Jump, one more, this one. This one. So I'm coming in here, I'm making this change of variable in order to do this integral. I want to point out right now, I've given you the change of variable, right? I've told you what we want to change to. If someone had just given you this problem right here and asked you to figure this out right here and not given you the change of variable, what would make you go and do this, right? What would make you change it to that? So we'll talk about that in a second. But let's just assume that someone gives us the change of variable and let's try and see how this problem becomes easier. All right, so let's set this up. We're going to start by drawing the region that we're trying to integrate over first. All right, here we go. So I'm trying to do a double integral over d of 4x plus 8y dA. That's what I'm trying to do. But I'm trying to do it on this parallelogram. I'm going to use my little grid in here to help me graph this. Where the vertices are at -1, 3, 1, -3, 3, -1, and 1, 5. All right, do you see the challenge of D? Do you see that it's not a very pretty type 1 or type 2 or polar region, right? It's a little complicated. Now, could you do it as type 1? Could you break this thing up? Yeah, you could. You could come in here and you could probably split it right there, couldn't you? And you could do this one as its own region and then this one as its own region. Put the two answers together. Agreed? Type 1, you would have a certain thing on top here and then on bottom here, and then on the other one, certain thing on top and certain thing on bottom. So we could do it that way, right? But let's see if this change of variables that's been recommended to us somehow creates a better region in a different space, different coordinate system. Well, let's do something before we convert over. Let's actually find the equations. These are little line segments, aren't they? Those are line segments. Let's try and find the equations of those lines that create those line segments. So what are they? Well, this point right here is -1, 3, right? And this point right here is 1, 5. It looks like it has a slope of 1, right? From my drawing, a slope of 1. What's the y-intercept? 4? Do y'all agree? Yes? But if you couldn't just look and see, if someone gives you 2 points, you can find the equation of a line, right? Not the vector equation, but the good old-fashioned college algebra equation of a line. Okay, so this should be y equals x plus 4. Yes? And then what about this one down here on the bottom? Where would that hit my y-axis? -4? And so the equation of that would be y equals x minus 4, right? What about this one? What's the equation of that line? Y equals -3x because it goes through the origin. So y equals -3x. And what about this one over here? -3x plus 8. Y'all see that? Now, let me take this equation on the top, okay? Let's move our x's and y's to one side and our constants to the other. So how about I do this? I'll move the y over to make it negative y, and then I'll move the x to the 4 to the other side and make it negative 4. Do you agree that that would give me x minus y is equal to negative 4? Right? Do the same thing on this bottom one. Move the y to the right, move the 4 to the left, and you would get x minus y equals 4, right? Now, on these two, let's get our x's and y's to one side. What would we get? How about 3x plus y is 8, and what's the other one? 3x plus y is 0. Yes? Okay. So there's something subtle happening here that we're going to probably recognize in a little while, all right? But look at x minus y is 4, and up there x minus y is negative 4. Somehow I've created this expression here, x minus y is a constant, and up there x minus y is a constant. This one, 3x plus y is constant, 3x plus y is a constant, right? So let's see what happens. All right, so let's do this change of variable. I'm going to come in here, I'm going to do the one that they gave me. I'm going to replace all x's with 1/4 u plus v. I'm going to replace all y's with 1/4 v minus 3u. Yeah? So what I'm going to do is I'm going to try and do this double integral over d of my function, which was 4x plus 8y dA. This is going to convert to a new double integral over my new region S. And it'll be, what's 4x going to turn out to be for us? So I just replace that x with this. So it becomes u plus v. And then I have plus 8 times y. What's 8 times y going to be? 2v minus 6u. And then du dv. I still have to figure out what these are going to be, right? What my, Jacobian determinant. Forgot the most important thing. Jacobian determinant, du dv. What's wrong? Yes. All right, so does everyone see? I do the change of variable they gave me. This is my new integrand. I still need to figure out the Jacobian determinant. I need to figure out my restrictions on my new variables. So how in the hell am I going to do the Jacobian determinant? For Jacobian determinant, I need what? The partial of x with respect to u, right? Partial v. So let's do that right here. I'm going to do it all in one step. Partial of x with respect to u. What would you get? One over 4. Times partial of y with respect to v. So distributing this through, right? And then just take partial of that with respect to v, you just get 1/4, right? Then minus partial of partial of x with respect to v, which is 1/4 again. And then partial of y with respect to u, which would give us what? Negative 3 over 4. And then that's just 1/16 plus 3/16, which is 1/4. So in this particular case, when we do our Jacobian determinant, the thing we have to stick into our integral is going to be a constant, all right? That's what it's going to be. We're going to have to scale it by 1/4. Questions yet? What do I still have to figure out? My limits of integration, right? I need to figure out what happens here. We already know that in the first, if we try and integrate over D, our limits of integration would be weird because it's going to be a type 1. We would have to split it up. But my new limits of integration, I'm hoping, are going to be nice. So I need to figure out what U and V are, right? I need, for this new integral, I need U is between what and what? I need V is between what and what, right? That's what I need to figure out. Well, a good way to figure that out is to come up to your equations that had U and V in them and try and solve for U and V. Okay, take these and solve them for U, solve them for V. So what I think I'll do is I'll grab this first equation here and let me work with it down here. I have x equals 1/4 U plus V. I'll write the other one down also. 1/4 V minus 3U. Why don't I just scale everything by 4? A little easier to work with, both of them. Now, I can solve the first equation over here for U, couldn't I? I could solve this one for U. But I could also solve this one for V and solve this one for V. Which one looks a little easier? Solving them both for V? All right, let's solve them both for V. If I solve this for V, I get 4x minus U. Solve this one for V, I get 4y plus 3u. What can I do with those? If they're both solved for V, set them equal to each other, right? So I take that, set it equal to that, and I get 4x minus u equals 4y plus 3u. And that gives me what? If I can solve it for u, 4x minus 4y equals 4u. Divide everything by 4. X minus y equals what? U. U is x minus y, right? Once I know what u is, can I go get v? Yes? So now what I'm going to do that I know what u is, I'm going to take that answer, I'm going to plug it in. Let's say we plug it in right into this one. We get v is equal to 4y plus 3 times u, but u is 3x minus y. So v is 4y plus 3x minus 3y. All right? V is 7y plus 3x. Y plus 3x, thank you. And I want to highlight those. The reason why these are important is because, remember up here on our picture, we had said, hey, look, if you take these lines and you get the x's and y's on both sides, I said, look, 3x plus y is 8, right? And then I said over here, 3x plus y is 0, right? And then up here we had x minus y is -4, and down here we had x minus y is 4. Following it? So when we come down and we look at this, we were trying to figure out the restrictions on u. If my u has to be x minus y, and my x minus y up there was, what, 4 and -4? Then I know that u has to be between -4 and 4. And then my v is y plus 3x. That y plus 3x had to be between what? 0 and 8. So what I can do now is come up here. My u, I can erase this. I have question marks. My u is between -4 and 4. My v is between 0 and 8. That's what we needed, right? So we're at the end of this. We've got double integral. Will it matter which way I go here? It's a rectangle, so it doesn't matter. I go -4 to 4, go 0 to 8. What was on the inside? Did we ever simplify that? We never did we? What was that integral simplified? This right here. 3v minus 5u. 3v minus 5u. Then we had the Jacobian determinant, which was a 1/4. I'll just take it completely out of the integral. And then I have what? D. This does matter, the order here, because they're dictated by this, right? The u is between -4 and 4, and the v was between 0 and 8. So the inner one will be v, and the outer one will be u. And that is the converted double integral. Now you may argue that, hey, that might have taken a little less time had I just broke it into two regions, did type 1, you know. But this is just to get us kind of started with it. Make sense or no? The big question is, you know, how do you know to use that conversion? So I think that's what the next example talks about. By the way, this is the converted. That region gets converted over to this rectangle. -4 to 4, and then 0 up to 8. So if you aren't given the transformation, the integrand itself, the thing you're trying to integrate, might clue you into an appropriate transformation. Remember that linear transformations take lines to lines. So back here, when we had this parallelogram, can you all see that point moving along there? Notice that that edge always gets taken over to, you know, that edge got taken to the bottom edge there. If I move across here, let me go all the way to the top, other side. Then the top line there gets mapped from that line there. So linear transformations takes lines to lines. So your edges will go to the edges of your new region. If it's a linear transformation. What's a linear transformation? One that doesn't involve squares and cubes and square roots, as long as it was linear. The transformation we had before was like 1/4 u plus v or something. That is linear. So take a look at this one. Use the change of variable to find this. Double integral over d of e raised to the x plus y over x minus y dA, where d is this trapezoid. So, what's that? What? No, that's not the way you spell trapezoid. Can't do anything about it now. It's printed on 100,000 copies of stuff, so. That's the way I spell trapezoid. It's not the way you're supposed to spell. All right, so here we go. Before we do it, though, take a look at this. Is that something you would want to try and integrate with respect to x or y, right? Wouldn't exactly be the easiest thing to integrate. So let's take a look at our region of integration. Our region of integration is this trapezoid. It's different than a trapezoid, all right? All right, 1, 0. Oh, that's overkill. I don't need that much. One, 0, 2, 0, 0, -2, 0, -1. Okay, here we go. You see two parallel lines there? So that should be a hint to us. Since they're parallel, they have the same slope. If I use a linear transformation, I should be able to somehow get those lines mapped over to constants. So let me take this. What's the equation of that? Y equals x minus 1. This one here. y equals x minus 2. If I take those and solve, in other words, get x and y on one side by themselves, it doesn't matter which way you go here, but I'll keep my x positive, okay, just as convention for myself. This is x minus y equals what? 1. This one down here, x minus y equals 2. So isn't it looking like x minus y might be a good transformation to use, right? Replace x minus y with maybe u or something like that. That would be u as 2. The other one would be u as 1, wouldn't it? Okay. What else? How about the other two lines? Okay, this one is y equals 0. And this one right here is x equals 0. So what do you think about that? What's that? Wait, I can't hear you. Okay. You're whispering. That's a little different, isn't it? Okay, well, let's see if there's, maybe we can squeeze the answer out of this. We just said maybe letting u be equal to x minus y, right, would work. So I would be able to come up to this integral. I'd be able to replace that right there with u. So what about the top part, x plus y? Maybe we just let that be v and just see what happens. How about that? What if we let v be that top, x plus y? What would our new integral start to look like? Double integral over s of e to the v over u? Would you be okay integrating that? That'd be a little easier to do, right? Because the u and v are completely separated. The problem with that one on the left is that the x's and y's are mixed in the numerator and denominator, so that's going to be a little harder to go backwards from. Okay, so next thing. What? Jacobian? You want to do Jacobian? Well, the u I chose because I noticed that these two would be between constants, 1 and 2. The other one was kind of like, well, it's the only other thing left. Let me try it and let's see. Sometimes it's a matter of you look and, oh, it's kind of obvious. And other times it's a matter of, okay, well, let me just go with what's there, try it, and if it works, it works. But we'll deal with the restrictions. We still need to know what our u and v are going to be stuck between, right? For this integral up here, this double integral, I still need my Jacobian stuff in there. I need Jacobian determinant, and then I need du dv. So I'm asking you, do you want to get Jacobian determinant now, or do you want to try and get those limits of integration? Jacobian? Okay. What do you need for your Jacobian? dx du, but look at what you have here. Right? You have it solved for u, not x. You agree? So here's what we're going to have to do first. We're going to try, and we're going to take the first equation up there. It will become x is u plus v, right? The other equation is what? X is v minus y. What am I doing? Go back to the previous problem. When we did Jacobian on the previous problem, weren't our equations solved for x and y and they were in terms of u and v? Now we have our equation in terms of u and v, and we need to go and get them in terms of x and y so we can do these partials. Understand? So that's what I'm doing right now. So I can set these two equal to each other. U plus y is equal to v minus y, which means that, what? U minus v, let me go the other way with that. 2y is v minus u, and then what should I do to get y by itself? Scale it by half? So this is one of the equations I can use that I'll take partials of. How do I get the other one? How about we take this right here? X is equal to u plus y, but y is 1/2 v minus u. So x is u, not u, what is it? Half u plus half v. That okay? Now let's go and get our Jacobian determinant. So Jacobian determinant, magnitude, is magnitude of partial x with respect to u. Right, that's the first thing we do, partial x with respect to u, which is 1/2, times partial y with respect to v. We got 1/2, minus partial x with respect to v, which is 1/2, and then times partial y with respect to u, which is negative 1/2. And so we get 1/4 plus 1/4, which is 1/2. So we're scaling everything by 1/2. So here's where we are. Got this, e to the u over, was it u over v? V over u, right? V over u. And then we had times 1/2, that's going to come out. And then du dv, what do I still need? My limits of integration. So I have to go back up to that picture, take a look at that, right? We said that our u was x minus y was between 1 and 2, right? 1 and 2. So I'm going to go down here, I'm going to say u is the inside one, between 1 and 2. U was between 1 and 2. What about v? How do I get v? Between 0 and 0, can't be that because we'll get nothing for the integral. Any ideas? Look at this line right here. Look at this line right here. If you're on this line, it gets mapped over to another line, doesn't it? We said linear transformation, you go line to line. If x is 0, what's your y between on this line? If your x here is 0, your y is still between what? Negative 1 and negative 2, right? So look at, we're trying to find out what's happening with v, right? This is the one we're looking at. If x is 0, right? If this is 0, what's v between? If x is 0, that becomes just y, right? And what do we say y was between? Negative 1 and negative 2, right? So it looks like it's between negative 1 and negative 2. What about this line right here? What if y is 0? What would happen to this if y is 0? You get v is x, right? And what's x? What is the x value? Between 1 and 2? We can only have one limit of integration, right? What about, no. It might help if we look at this line right here, okay? Look, we said y is equal to x minus 1, right? That was just got the slope, and we figured out what it was. Then we switched it over. We said x minus y is 1. So we said along this line, right, if x minus y is u, then this thing constantly, this equation always has to hold to be 1, right? And then on this one, if we're any point, any x and y on this line, it has to be equal to 2. Yes? So if we're on this line right here, right, if we're here, then what has to hold true? Anywhere on this line. The y has to be 0, right? If y is 0, then you get what? You get just x. How do you mean? There's let me try something, a little different approach to help us see what's going on here. We have a new, this might be a lot easier to see. Give me a second. We are trying to convert that weird region into a rectangle, aren't we? So if this is u and this is v, what did we just say u had to be between? -1, right? And what? -2. My u is between -1, -1 here, and -2 here. So it can be anywhere between here, right? With me? So it can be anything in there. U is between -1 and -2. Now my V should be something like between two things that will close off this rectangle and give me my new rectangle. Yes? Do y'all understand? I'm going from a rectangle, I'm trying to go to a rectangle with this conversion. Pardon me? Is it between, but where's y and x here? So if I bring up that other picture over here, we were looking at, it was between here and here, right? Right there? Everyone said that was x equals 0, but the y was between what? -1 and 1? Or -1 and -2 and -1? If x is 0, where's your u? Remember what u was? It was x plus y, right? If x is 0, what's u? That was for v, though, right? Or was it the other way around? We are doing v, but I'm saying what was u? U was x minus y? Okay. What I'm trying to say is we know where this piece went, right? Where did that piece go? Where did that one get mapped to? Okay, to this one right here, right? Where did this piece go? Right there, is that one, right? That one right here, didn't it? The question is, where does this green one go? Well, if we're having trouble, why don't we just take this point right here and try and figure out just where that point goes? What's that point right there? 0, -1? Yes? We don't have to worry about the y equals 0. Right here, I haven't done that yet. This part, yeah. What I'm going to do is, I'm trying to get you to see that finding the restrictions on the U is relatively easy, wasn't it? Yes? The V is a little different because I can't get the equation to match up just perfectly. So what I'm going to do instead is I'm going to try and figure out where just that line segment goes by figuring out where the two corners go. Yes?
Oh yeah, I was gonna say, can you set your U equations equal to each other, and then solve for x and y that way, plugging in the point?
Well,
Find your balance of V that way.
maybe. But when your U's are equal to each other, that means when these two are equal to each other. So
Well, I guess in the y portion of n,
just take that corner point. X is 0, y is -1, right? Okay. What do you get for U when you plug that in? What do you get for U? And then we'll do V in a second.
1.
U is equal to 1, right? U? No. Yes? This isn't making sense. What's V? X plus 1? So what do we get there? V is -1, right? It's -1's right, but why is U off? Hold on. What was our U? What are our points? 0, negative. What was that? 1 and 2. 1 and 2. It's 1 and 2. Look, it's 1 and 2 here. Yeah. Well, I asked, was it -1, -2, and no one disagreed. I didn't go back to my notes. Okay, look, these are on the wrong side. They're 1 and 2. And it's the red one, right? The red one is here. And then the blue one is here. That's 2. What's that? You have 2 axes, right? Here. There. Okay. Where does that point go? Where did that point go? 0, 1 went to 1, -1, which is here, right? Where does this point go? That's the point 0, -2. 1. What's U? 2. What's 2, -2? 2. Yes? All right. I think I've lost everyone pretty much. All right. Let me write down the 2 equations for U and V. What screwed everything up was the lines were on the other side. U is equal to x minus y, right? V is equal to x plus y. Let's find out where these 4 corners go. If I plug in 0, 0, 1 in for this one, U is equal to, if I plug in 0, -1, U will be equal to x minus y, which is 1. My V, which is x plus y, will be 0 plus -1, which is -1. So that gives me that point right there. Yes? Okay. Now, plug in 0, -2. If I plug in 0, -2, I get U as what? 0 minus -2, so that's 2. V is equal to 0 plus -2, which is -2. So I go out 2, down 2. Okay? Big deal. It's not a rectangle. It's okay. It's a linear, right? Now, what about these points over here? 1, 0, and 2, 0. Where do they go? So if I plug in 1 for x and 0 for y, what's my u? 1. What's my y? What's my v? 1. So I go out 1, up 1, right? If I plug in 2, 0, what happens? 2, and then 2. I get up here, don't I? Makes a trapezoid like this. So I've gone from a trapezoid to a trapezoid. But what? This one's, it's like a type 1, right? So are you going to be able to put in your new integral, are you going to be able to do between two constants? You're going to be able to do your u's between two constants, right? But your v is between what? Well, everything's in terms of v and u now, right? So what's the equation of this piece right here? V equals u, right? What's the equation of this one? V equals negative u, right? So our new region, I said it would be better. I didn't promise a rectangle, but it would be better. And you might, I never said it had to be a rectangle. I said it could be. Linear, I said lines go to lines, so that's the only thing we've got. This one we'd have to break into two different regions. That one's just one integral. So let's try and finish up what this damn integral is going to be. My u is stuck between two constants, 1 and 2, right? Not negative 1 and negative 2. V is stuck between where? Negative u and positive u. So my double integral becomes double integral from 1 to 2, from negative u to u, e to the v over u, d v d u. And then the 1/2. That would be it. All right, so let me just kind of recap a little bit of the approach to this. If you can get some of the sides of your region, right, if you can get them to become equations where you get the same thing in there like this, and they're equal to constants, that's pretty much going to dictate what you should use, right? The other one, well, you might just have to go with what's left there like we did. But your new region, right, wherever this goes to, if you have trouble figuring out what it looks like, you can always take, if it's a linear transformation, you always go corners to corners. So every corner has to go to every corner of your new picture. So it's just kind of a trial and error thing. The problem we did before this, the region was so nice because we were stuck between two constants and it was obvious from the algebra what they were. We didn't need to draw a picture and try and go corner to corner. I hope that makes sense. Mm-hmm. If you know your u and v equations if it's a rectangle, yes. Are you saying if it's like, then I'm a little confused as to your question. If you know, like we knew our u and v equations, we have them right here. Transformed, yes. Uh-huh. Okay. How do you plug the edges in? I'm not quite sure what you mean by plugging the edges. You mean to plug in the corners? Oh, okay, plug in the vertices. You can plug in the vertices, yes. Yes, that would work. Yep. Yeah, when you were saying edges, I was thinking you were talking about the entire line. Yeah, okay, that would be hard to. Okay, that's going to wrap up chapter 12. There's a few problems I believe that I put here for you to try. Those are the correct problems, wrong page. Does your take-home have a problem like this? It does, doesn't it? Don't you have a change of variables problem in here? What number is it? Is there not a change of variable in here? No? I don't see one. Okay. Show them the last page of the notes. All right, we're going to start 13.1. Vector fields. So a vector field in two-dimensional space. Let D be a set in the plane. A vector field on D is a vector function, capital F, that assigns to each point x, y in D a two-dimensional vector f of x, y. So here's what's happening. You take some point in this space, or you define an actual vector field right here. F of x, y is negative y, x. Negative y, x. So this vector field is negative y, x. So if I plug in to this vector field, if I say, hey, go to the origin, 0, 0, right? What does this vector field spit out at 0, 0? Or what is it doing at 0, 0? 0, 0, right? Which is a vector. So at the origin, imagine the point at the origin, there is a vector associated to that point, and it is the 0 vector. If I say, okay, move out the x-axis 1 unit to the right, what's happening there? What's the vector at that point? Well, it's negative y, which would be negative 0, and then x, which is 1. And then if I go out, 2 to the right and don't go up and down, I have a vector that's, 0, 2? Both of these vectors, these two vectors, point which way? Straight up, right? So back here, what I'm doing is I'm saying, look, at the origin, I have the 0 vector. If I move to the right to the point 1, 0, which is right there, it's at that point there's a vector 0, 1. If I move to the right to the point 2, 0, there is a vector at that point 0, 2. Yes? So for every point in the space, there is a vector associated to that point. If I went out to the 4, 0, it would point out 0, 4, wouldn't it? Now what happens if I start throwing in something a little more interesting, like if I go up, let's say I go up 2. So at 2, 2, if I come in here and say, all right, what's happening at 2, 2? It's saying, all right, the negative y is negative 2, and then x is 2. So that's a vector that points to the left 2, up 2, right? Left 2, up 2. And that's, you can see here with this picture, to left 2, up 2. Yes? Okay, so that's the general idea, is that at every point in the space, you have a vector associated to that point. And you can look at it like a person standing there and wind is blowing or something, right? I'm standing here and there's wind blowing, I move and the wind is pointing, different direction, different strength, or magnetic fields, things like that, electromagnetic fields, different places, it has different strengths, different directions. So what we can do is we can try and show you all the vectors for every point, but that's impossible, right? It'd be impossible to show you every point's vector. What would happen if I show you every point's vector here? it would just be black, wouldn't it? Because you would have a point, every point would be represented with something, so it would be black. So what we do is we tell the computer, well, show us a pretty good representation. So pick a couple of 100 points and show me the vectors at each one of those points. And when we do show you a couple of 100 of them, then you start to get a feel for what this vector field is doing, right? It looks like this vector field looks like it has some sort of rotational property to it, right? Looks like everything wants to get turned counterclockwise. Now, what do the bigger vectors mean? As you move away from the origin, right? Those vectors are getting bigger, right? So if it's wind or something, this would be kind of opposite of a hurricane. Isn't it stronger in the center? Stronger? Right? Okay. Yeah, so I don't know. Well, no, the wind on the outside is moving fastest or the inside? Then you have the eye wall, which is where it's calm. Whatever. We're not meteorologists, but the idea of this is... What? You get the idea, though. This can represent a real situation. How could I make it reversed? How could I make it stronger in the middle and as I move away get weaker, but have that same rotation on it? Square 1 over it. Reciprocal would do it. As I move away, it would get smaller. As I move closer, it would get bigger. That might work. But what happens at the origin? Ah. Yeah, it's undefined, right? So you would just, that would be like this, goes off into another dimension, some other world, universe somewhere, right? Okay. Now I could have the computer do even more. Give me lots and lots of points. I don't know what happened. Didn't look any different, did it? Oh, wait, there it goes. There we go. That's a lot more, right? You still get the same idea, though, right? Now, that's just for that particular, vector field. If I change the vector field, it's going to do something else, right? So what about a different vector field? I've got another one here that I can just type in my own. So what do you want? You want 1 over x? Let's try that. I'm going to get undefined, so why don't we do this? If I always want to stay defined, could I do this? 1 over x squared plus 1. Won't that always keep my denominator defined? Yes. And then over here, 1 over y squared plus 1. See what happens. I'm just making up our own vector field. And I'm going to show a coarse representation. Now, I don't think we're going to get... I wanted some wrapping action. Yeah, the square's kind of messing that up. Let me see if the computer's going to be able to handle the 0. I think it's going to really not like me when I do this. Yeah. Let's see. It had some trouble. It was really big here. It's a big vector. Do like a, well, yeah, you could do that. We're just playing now, right? Abs plus 1. What's the moral of the story here, though? I mean, you can create pretty much any vector field you want, right? Can't divide by 0. Okay. It doesn't matter. The idea here is that for two-dimensional space, you can somehow define a function that spits out vectors at every point, and all these together creates what's called a vector field. Now, as you might imagine, you can do the same thing in three-dimensional space. For every ordered triple, you can assign to it some vector, and then you would have something, like, here we go. I just have a particular vector field, and as I move through this vector field, you can see my vectors pointing, changing directions, right? As I change the x, y, and z coordinates, my vector starts pointing in different directions. So this is even better for real world stuff because we live in 3 dimensions, right? So you can imagine an actual particle sitting there getting blown around through something, and you know, the vector being which way it's pointed and how fast it's going in that direction. Or again, magnetic fields, fluid flows. So now I'm going to show that vector field. And as you can tell, this is Mathematica's best attempt. That automatic looks pretty cool. You could kind of see some of the behavior, right? If I start trying to rotate this, it gets hard to see things, you know? It really gets hard to see things 3-dimensionally. And if I wanted to, I could really try and bring my computer to its knees by clicking fine. Let's see what happens. There it is. Okay? All right, so you have this idea of vector fields. So for this one, it says sketch the vector field negative x over square root of x squared plus y squared plus z squared, right? Negative y squared. What do you recognize? What is square root of x squared plus y squared plus z squared on the bottom? Okay, it's the distance. It's a unit length. So look, take the vector field. If I gave you a vector field negative x, negative y, negative z, right? If I gave you that, as you moved around, the further away you were, the bigger the vector would get in certain components, right? But what if I say come in here and scale it by its own length? What would you divide through these by? You do the magnitude of this, which would be what? The square root of this square plus this square plus this square, which is that, right? So this vector function is always going to spit out unit vectors, isn't it? Unit length. And they will always be pointed negative x, negative y, negative z direction, which turns out looking like this. Let me move the point around first. Can you all see this point? That point, notice the vector's length is never changing. And notice what it keeps doing. It's always wanting to point to the center. Might be hard to see that until I throw the actual vector field in there for you. Have the computer show us a bunch of points. Oh. That's maybe a little overwhelming, but all right. That's still overwhelming. But you see, all the vectors point to the center. That's a good vector field for what type of situation? Gravity, right? Gravity. Now, we all know the closer you get to the center, right, the stronger the gravitational force is. But you could at least use this vector field on a sphere where you say, okay, every point that's equal distance should have the same gravitational force, right? So that's a good type of vector field for gravity. Okay, so gradient vector fields. Recall that if f of x, y is a scalar function of 2 variables, then we define the gradient. Remember the gradient as the partials? It's a vector created from the partials. In 3 dimensions, the gradient was the partials. In either case, the gradient of f defines a vector field, which is called the gradient vector field. All right, this is going to come up more later, so I want to make sure you understand at least the language here. If somebody gives you a function of 2 variables or a function of 3 variables, if we take its gradient, we create a new function, a vector function. That vector function is called the gradient vector field. All right? So given this function, f of x, y equals x squared y minus y cubed, find the gradient vector field. So what's the gradient vector field for that one? I'll just write it down on the board. What's the gradient vector field? And we'll call it capital F. 2x, 2xy, and x squared minus 3y squared. It's a great marker here. Now that I could say is a vector field, right? And I could say for every point on the plane, I have a vector. So imagine now that this is the plane that I'm talking about, and I'm going to define a vector field on this plane, and that vector field is going to be that gradient vector field, all right? What does it look like? What I would like to try and see is what is the relationship it's not necessarily a tangent vector. It points in the direction of, remember what the gradient always did? Greatest ascent, right? Greatest rate of change. So here's that function we started with, right? It's this weird, sheet flapping in the wind here. And then if we look at it from the top, the gradient vector field looks like this. And notice that as you get further away from the origin, those vectors get longer, don't they? So what's happening is it's saying that if you're on this sheet and you start moving like backwards this way, okay, going that way where it starts to go down, right? The steepest descent would be if you turn around and go back the other way, right? That's what these are saying. It's saying as you go that way, turn around, point the other direction, that's your steepest ascent. Or if it says if you're caught somewhere here on the side, right, which would be somewhere over here, one of these sides, then you're trying to go up that hill. It tells you steepest ascent, you're going to have to be kind of at an angle coming up that. Does that make sense? Yes? Okay, conservative vector fields. A vector field F is called a conservative vector field if there is some scalar function little f such that capital F, the vector capital F, is equal to the gradient of F. This just means the vector function is the gradient vector field of some function F. All right, so if somebody gives you a conservative vector field, if this is a vector field, right? Right here. This is a vector field. Is it conservative? Well, is it the gradient of something? Yeah, we just did that problem, right? Right before this? I gave you a little f, we took its gradient, it spit out this. So if you look at a vector field in general, and you say, okay, did that come from the gradient of something? Then if it did, it's conservative. Got it? It's not at this point easy for us to check whether or not something is conservative. We'll have a real easy way later. That's it for that section. It's just introduction to vector field. Those problems are correct. Page is wrong. (13.2). I know we're going to get a little bit ahead on our calendar here, but that's okay. Never. Oh, you know this Thursday is the last day to drop the class, right? Just so you know. You get a W if you drop. Okay, line integrals, or called curve integrals. All right, suppose we have a function f of xy defined on a curve C in two-dimensional space. So here's our function. Our function of two variables is a surface, right? We restrict that surface to a curve. So on the ground, the domain is this little semicircle right here. If we map just those points up into the function, we get that blue path on the surface, right? We wish to find the area if we drop like a curtain coming down from that curve down to the ground, like that. We want to find that area. See, it's not a volume, right? We're not integrating over some solid region in two-dimensional space. We're integrating over a curve on the ground and then up into the function. And then dropping that down and finding the area, surface area of that thing. Understand geometrically what we're doing? So remember in Cal 2, what we did in Cal 2 when we wanted to find the area under a curve, right? We had the function here. Then we had our interval from A to B, right? We broke it up into a bunch of little rectangles. We said that the width was what? Dx, right? Let's see my picture. Yeah, no. So on the integral back in Cal 2, the dx was the width of the rectangle. But for us, we're going to break this little curtain up and notice that the width of my rectangle is not dx. Because this is my x-axis, right? So, and this is my y-axis. So that little length of that rectangle isn't dx or dy. It's actually the arc length of that red curve, isn't it? It's the arc length of that curve, which is why when we do this line integral, is we say we're going to do the integral over c is a curve, of this function d little s. And d little s is this. It's the infinitesimal arc length. Do y'all remember this formula for arc length? It's a Cal 2 formula. The formula for arc length is the square root of the derivative of y with respect to t squared plus the derivative of x with respect to t squared, dt with respect to time. Okay? The picture is this, if you want to see it visually. What it is, if this is x and this is y, we're looking at that red thing on the ground. We picked 2 points that go up, right? So this is our approximation. Looking at it from this side, here's x, here's y, here's that little arc on the ground. We're taking these 2 points and we're creating just a rectangle right there, like that. Okay, up into the surface. That little piece down there is this little piece, which is arc length. So we imagine a little right triangle. This is like dx, this is like dy. So this piece right here would be square root, right? A squared plus b squared is c squared. So that side would be the square root of dx squared plus dy squared. That's pretty much what's happening there. All right, now, in order to do this, we're going to have to find parametric equations for x and y and have some restriction on t. Remember parametric equations. It's like you can draw a curve. You start your watch, it starts drawing the curve, right? You stop your watch, at some point it stops. You get some curve in 3 space or 2 space. We need to find those parametric equations to be able to do these line integrals. So once we do that, we're just going to grind out the integral. This is called a line integral with respect to arc length. The ds is the arc length. Now they call them line integrals, but it's not a very good name because most of the time we're not integrating over a line, we're usually integrating over a curve. So that's why in the beginning of this I said line integrals, curve integrals. Because by the name, you might think, well, I can only integrate over a line for this to work or something. So here we go. We'll do our first one. Find the line integral over C of this thing, ds, with respect to arc length, where C is the upper half of the unit circle. So what's the first thing we have to do? Okay, dx and dy squared. But in order to do that, we have to find a parametric representation for the curve. Okay, so what's our curve, C? It's the upper half of the circle, right? Upper half of the unit circle. So here's a picture. 1, -1. Can anybody find me a parametric representation? In other words, can you write x as some function of t? I'll call it f of t. Can you write y as some other function of t? You could also say x of t. You could also say y of t. How can I draw that red circle? Cosine sine, right? Almost like polar. But do you need the radius to be r, or can it be fixed? It can be fixed. The radius is 1, right? So this could just be, the x could be cosine, but we can't use theta. We have to use, we're going to use t as our parameter. And then our y will be sine t. And our t will be restricted between where and where? 0 to pi. Everyone agree with that? If I replace x with cosine t, replace y with sine t, let t go from 0 to pi, I will draw that red curve. Yes? And it will also draw it. Let's talk a little bit about direction, even though it's not going to be important right now. The direction of the drawing of that curve, if I go from 0 to pi, it will draw this thing counterclockwise, won't it? Okay. Now, to do this double integral, this integral, what I need to do is do the integral. Now my restriction on my integral over c is just the restriction on my variable. So what's the restriction on my variable t here? 0 to pi, right? Then I come in here and I say 2 plus, what's x squared? Cosine squared t. This then times y, which is sine t. But then not ds, I need to replace ds with what ds is. ds is the arc length. What's the arc length? Square root of dx dt squared plus dy dt squared. Well, here's x, right? Here's x as a function of t. What's derivative of x with respect to t? Negative sine t. And then square it. So I'll put that in here. Negative sine t squared plus, what's derivative of y with respect to t? Cosine t squared. So cosine t squared. And then you can throw in here dt. Yes? And that's real nice because that all just turns into a 1, doesn't it? So you're just now at integral 0 to pi, 2 plus cosine squared t sine t dt. And that, I think you would agree, is a pretty straightforward integral, right? That's just a cal 2 integral right there. So I will let you have the rest of that. But what does that represent? Like geometrically, what is that? Area under that curtain, right? So you take that semicircle, you map it up into the function, and drop a curtain down. That's the area of that. Questions? I think the hardest part of these is getting the parametric equation for the curves. That's going to be the hardest thing. Okay, what if you have your curve on the ground is actually a bunch of curves put together? So C is the union of a finite number of smooth curves, C1, C2 through Cn. Then if you want to do the line integral over C, you can break it up into a bunch of different line integrals, each one over each of those curves. For example, if I have a curve, see my curve on the ground is that red thing? It's actually a parabola that goes from the origin to 1, 1, which is right here, and then a line segment that goes from 1, 1 to 1, 2. You take all those points, you map them up into this plane, you drop the curtain down, and you're trying to find the area of that thing there. Well, if that's what you're trying to do, you can just do it as two separate integrals. The integral over C1, the integral over C2, add the answers together. So I'm going to do this one. And then I'm going to give you one. I think I might give you two problems to do as an in-class quiz. All right, so here we go. I want to do integral over C of 2x ds, where C1 is y equals x squared from 0, 0 to 1, 1. And then C2 is the segment that goes from 1, 1 to 1, 2. So we have? Yeah. All right, let's start with C1. What you need to do is figure out parametric equations for x and y. And we're trying to draw a parabola that starts at 0, 0 and goes up to 1, 1. And they even gave you that it's y equals x squared. So how do you find a parametric equation whenever you already have the equation solved for y like that? What can we do? Did we talk about this? How you can do that? How many of you have a graphing calculator that has parametric mode on it? Right? Parametric mode allows you to do things like this, draw things like this. Y is just x squared, isn't it? So what if I call x t and I call y t squared? Wouldn't that draw exactly what I want? I mean, think about it. Any point on here has the coordinates x squared, doesn't it? X is what I plug in. What comes out? Y, but what's y? X squared. So I replace that with t and that with t, then I'm just changing the variable. You get t and t squared. Y'all follow that? What's the restriction on t? Between 0 and 1. So for C1, there's the parametric equations for x and y. There's the restriction on t. So let me set up the double integral for that one. I keep on saying double integral. Let me set up the line integral for that one. We're going to go from where? 0 to 1. What are we integrating? 2 times x, right? What's x for us? Just t. then square root of, here comes my ds, derivative of x with respect to t, 1, and then squared, plus derivative of y with respect to t, which is 2t, but then squared, so 4t squared, and then dt. Does everyone understand where these pieces came from? One is derivative of x with respect to t, squared. The 4t squared is a derivative of t squared, squared. And then dt. And then you could do this, right? Just a u sub right here. Let that be your u. You've got pretty much derivatives sitting out there. You have to work through it. So dot, dot, dot. You get that answer. Now we have to do the line integral over the next part, C2. And then add the two answers together. So C2, I'm going from 1, 1 to the point 1, 2. So I'm talking about, I want to go from 1, 1 to 1, 2, like that. Any ideas? What's that? Y equals t plus 1. X is what? X is 1 and t plus 1. So how are you getting that? Just kind of mentally? Yeah, your x values are always 1. And then your y's will start at 1 and then end at 2, so you could say, you said t plus 1? Okay, that is a way of doing it, just like a mental check, but let's go back to chapter 10. Do we know how to find the vector equation of a line? Do you know how to find the vector equation of a line? R of t equals r naught plus tv, where r naught's 1 point on the line, converted as a vector, the v is the direction vector. And I said if you ever want to do a line segment, you can do a line segment. You can let your t go from 0 to 1, right? But you have to do it a certain way. I said that, yes? So someone give me the vector equation of this. R of t equals, where's my r naught? 1, 1, because I want to start here, don't I? So 1, 1, I'm going to write that as a vector, 1, 1, plus t times v. What's v? The direction vector, which is this point, take away this point. So what would that give me? 0, 1. And when I put those together, r of t equals, what, 1 plus t? And then remember when we had the vector equation of a line, we said you could convert the vector equation into the parametric equations and the symmetric equations, remember? Parametric and symmetric. Well, parametric is what we want, right? So x will be what? 1, and y will be, and our t is restricted between 0 and 1, right? That should draw me that line segment. So my x is 1, my y is t plus 1 or 1 plus t. My restriction on t is 0 to 1. Yeah? And so this integral is going to go from 0 to 1. It's going to be 2 times x, right? What's x here? 1 times the magnitude of, the square root of derivative of x with respect to t, which is 0, so nothing there, plus derivative of y with respect to t, which is 1, but then squared, so 1, then dt. So it's just a 1 there, isn't it? This is the integral from 0 to 1 of 2 dt. And that's going to require a very advanced technique of integration. So take your time on that. Don't get a headache. You take the two answers, you put them together, right? So part of what that problem is about, just to remind you how to get line segments, right? I would only be careful if you're going to do it mentally I would only be careful with this, okay? Because if you want to go between 2 points, in general, you got to make sure 0 to 1 is going to work, you know, and you might have to adjust something if you do it mentally. All right, let me just see what else was next here. So there it was. Yeah, I think that's a good place to break. So it's 310. It feels like Monday. Take a look at your take home here. If there's anything you can actually do on this. No? First one? That's about it? Yeah. I think it's due next Wednesday. Right? I think it says it on there. It's due next Wednesday. So you have a week and a half. How about we do a quiz, because we need another quiz grade. So why don't we do a little in-class quiz? I want to see how you can do with just you and your notes right now, okay? So you can work on this by yourself, but you can use all your notes and anything you've written down. Fair? Okay. Let me get something here. So I'll let you choose. Do y'all want a Lagrange problem? No? Okay, here we go. So you'll turn this in at the end, right? You'll turn it in, so make sure you do it on blank paper, like get your own paper out and everything. For the first one, set up the integral. Set up integral. When I say set up integral, that means do not evaluate it, okay? Just set up the integral, which is gives the volume of solid under x plus 3y minus 4z equals 10. And above this region. I'm going to draw a picture. The region is this region right here. I need some room to write. The next one, you're supposed to set up an integral that gives you the volume inside the unit sphere in the second octant. What is the volume? I want the integral. And don't evaluate it, just set it up. That'll be it. We'll just do that.